Hello there, welcome back to Differential Equations by Alexander. So today we'll continue talking about the vibrations of a mass on a spring, and then we'll deal with the free damped motion case. And damped means the following, so I'm going to share a photograph here. So this is something that I Google from online, and so if you Google car suspension, then this is something that you'll get there. So I'm just trying to give out some credit there. And then what I want to focus here is on the coil spring. And so this is part of the suspension. So the coil spring is in yellow in the car. And now the thing that I want to focus on for today is that you also have these blue cylinders, and those are called the dampers. Sometimes they're called the shock absorbers, so dampers. So you have two of them. So two blue cylinders and two coil springs. And so this is what helps your car have a smooth feeling to it when you drive around. And so we are going to consider three cases. The three cases physically means that you have a good suspension, so there's nothing that you need to do to the car. The second case will be the case where you probably need to do some work to the suspension because you need to replace either the coil spring, the damper, or the entire thing together. And the entire thing together is the third case will be where the suspension is bad and you need to do some fixing on the car. And so that's what we're going to deal with today. Okay, so I just want to give you a physical reference to what we're dealing with mathematically. And so now let's go back to the mathematics. And so the situation that we have is the following. We actually are looking at the second equation for today. This is the free, which means that there's zero external forces. Damped because the beta is actually a positive number, means that there's a beta here in the equation. And so the problem that we have is the following. We have this differential equation, and then we want to solve the differential equation. And so what we're going to do is we're going to divide by m everywhere. And so if we do that, then we get the following equation. We get x double prime plus beta over m x prime plus k over m x is equal to 0. And then in order to simplify the equation or the mathematics, we're going to do the following. We're going to make 2 lambda is equal to beta over m. And then we're also going to make the omega square equal to k over m. So we're making this we're making this identities to simplify the mathematics. And not only that, but omega does also have a physical meaning to the situation that we have. We'll talk about that later. And so when you do that, you get the following equation. You get x double prime plus 2 lambda x prime plus omega square x is equal to 0. And so 2 lambda is a number that we do know from the physical situation because we know the damping constant and the m, the mass, and then we also know the k, which gives us the omega square. So this is lambda here, and then this is the x prime. All right, so now how do you solve this differential equation? Okay, so you assume that the solution is of an exponential format, and so you assume that the function x is e to the, say x is of the following format. This is r to the t power, and then we're going to assume that the number that we are putting here is the r. And so our question is, what is the r equal to? Previously we used m e to the mt, but I'm not putting m because m actually means mass for our physical situation, so I don't want to confuse the math and the physics. And so when you plug this into your equation, into your differential equation, then you're going to get your auxiliary equation after you do a little bit of algebra. So r squared plus 2 lambda r plus omega squared is equal to 0. And again, the question is, what is the value for r? What is the value for r? And so this is a quadratic equation in the variable r. And so that means that we need to use either we can factor this or we can use the quadratic formula. That we can always do that. And so the situation that we have is the following. So I rewrote this just to kind of make it a little bit more clear. So you have the differential equation on the very top, then you have the auxiliary equation, and then you have the solution. After you use the quadratic formula, you get this r is equal to negative lambda plus or minus square root of lambda square minus omega square. And so this is after using the quadratic formula, you get this. But now, depending on what is inside the square root, we are going to get 3 different cases. So mathematically, we have the following 3 situations. Okay? So depending on the discriminant, if the discriminant is positive, then we are going to get 2 real roots for this for this r. So that means that we're going to get r1 and r2, so two real numbers, and that means that the solutions that we'll get are x1 is going to be e to the r1t, and then the second solution is going to be e to the r2, the second number multiplied by t. So those would be the solutions to our differential equation, or your linearly independent solutions. And now the second case would be whenever the discriminant is equal to 0, and that means that we are going to only get one number for our r, and so r will just be equal to just one single number. And so in that case, the solution to the problem will be e to the r1t, and then the second solution would be similarly, so r to 1t, the same number, but we have to attach a t. And then to know how do we get that extra t there, so that's where you do the reduction of order to get that second solution. So that's the second case. Now the third case will be a little bit more involved. So you have this discriminant, the thing under the square root, to be negative. In that case, you're going to get two complex roots. And so if your numbers are of the following format, you have some number alpha plus or minus I beta. Okay? And beta is not the same beta as we have here on the top. And so the whole point is this: the solutions are going to be in terms of exponential times cosine, so e to the alpha t multiplied by cosine of beta t, and then e to the alpha t multiplied by sine of beta t. The only tricky part here is that the beta that we have in the very bottom is not related to the physical system that we have. Okay, so we have to be very careful on how we write down our solution, but we'll talk about that later. Okay. So that's our second solution. But before I move on, I want to kind of go back to the physical situation. So right now, this is everything here in this slide. We are talking about the situation mathematically. So we're talking about the discriminant, and we have either these two complex functions in the red, or in the purple we have an exponential, and also the exponential multiplied by the polynomial t. And then on the very bottom we have the blue, which is exponential multiplied by cosine, or multiplied by sine. And so those are the format of the linearly independent solutions to the differential equation. But now going back to the physical situation that we have, which is the car suspension problem, we say the following thing. Okay, so the first case is whenever the discriminant is positive. In that case, we are saying that the lambda is bigger than omega. But then you have to remember that the 2 lambda, we made that equal to beta divided by m. And then the omega square, we have made that equal to k divided by m. And so the thing to focus on here is that lambda is essentially related to the beta. I'm not saying that the lambda is equal to beta. I'm saying that the lambda is related to the beta, and beta is the damping constants. And now omega, on the other side, omega is related to the k, and k is the spring constants. Okay, and so what we're saying in the first situation, we're saying that the damping, the beta, is bigger than the k, essentially. That's what we're saying. And so in other words, we're saying that the damping is much bigger than the spring constants. And so that's what we call this situation to be the overdamped situation, which physically it means that your car suspension is in good condition. It's like a mint condition. So that's something that you want on your car suspension. Now on the second case, we have the critically damp, and basically what this is saying is, roughly speaking, we're saying that the damping force is roughly equal to the spring constants. It's not exact equality there, but we're kind of saying that the damping coefficient is almost the same thing as the spring constant. So you are in the critical situation, which physically it means that your car suspension is still okay to drive, but it is recommended that you change your springs or your dampers or the struts. So you need to do a little bit of work. That's the recommendation. But if you want to continue driving, it should be okay, as long as you don't drive through some very rough terrain. Now the last case is the underdamped. This is where your car really needs some work, and that is the case where the damping coefficient is much less than the spring constants. So that's roughly what this means physically. All right, so I gave a little bit of physical meaning to this problem. Before that, we were dealing with the mathematical situation. And so now let's go back to the mathematical situation that we have. Okay. And so remember that we have three cases, and then all those three cases depend on what is under the square roots. Okay, so that's called the discriminants. And so let's go with the first case. Okay, so now here we need to be a little bit more precise. And so if if you consider the first case where the discriminant is positive, or physically where your suspension is in good mint condition, then your linearly independent solutions are going to be of this format. And here I kind of separated the e to the negative lambda t already. So those are your two linearly independent solutions because your formula for R is given by this. Okay. Now the second situation, which is called the critical damped situation, or when the discriminant is equal to 0, then you only get one real number, and then notice that the two functions are almost the same except that you have this extra t on the second solution. So these are the format of the solutions, and then those are with the specific numbers given to us. Now the third case is whenever the discriminant is negative, and that's going to give you two complex numbers for your R value. So your R number is going to be two complex numbers, two complex values. And so in that situation, we don't want to deal with a complex exponential functions, and so we change them into in terms of cosine and sines. And in this situation, this is what we have. Okay, so these are the formulas for the two linearly independent solutions. And so again, the first case is whenever your suspension is in good condition. So this is a good. The third condition is where the suspension is really bad, so you do need to replace your struts. The middle case is where it depends on how much you want to save money, at least for a little while, and so you don't have to change the struts just yet. All right, so now let's go into a specific example. So I'm going to tell you here that this is already I'm going to give you three examples, one for each of the three cases. So this is going to be the overdamped situation, and this is the case where your suspension is in good condition. So I'm telling you what the situation is before reading the example. So let's go through the wording, and then from the wording we need to translate this into the mathematical setting. And so the first part is going to be the following. So let's just look at the first sentence, and actually just look at the first part of the sentence. So a 32-pound weight. Okay, so what that means, you have to remember that the weight is actually a force. So this is the weight, which is a force, which is due to gravity. So this is going to be mass times gravity. The weight is a 32-pound force, and then this is going to be mass times gravity, which in this case we're going to make this equal to 32 feet per second. And so that means that the mass for our specific problem is going to be equal to 1 in this question number 2. So we took care of finding the mass. Now let's look at the second part of the sentence that we have here underlined. So we are saying that a 32-pound weight stretches the spring by 2 feet. And so now we're going to use Hooke's law. So Hooke's law, and then that tells us that the force that the mass does on the spring is going to be equal to Ks. So this is the force that the mass does on the spring. This is equal to Ks. And so the force is equal to 32-pound force. And then the stretching, S is the stretching amount, and then this has been stretched by an amount of 2 feet. So that means that the K is going to be equal to 16. Okay, K is equal to 16. So we use Hooke's law to figure out the spring constant K. Now let's go into the second sentence, at least just the first part. So assuming that a damping force numerically equal to 10 times the instantaneous velocity acts on the system, just reading that part, we are looking at the damping force. So damping force, and that's going to be given by F is equal to negative beta x prime. So that's what we said on 2 previous videos. And what they're telling you here on the sentence is actually that the beta is equal to 10. You don't have to actually solve for anything. They actually are telling you already that the beta is equal to the number 10. And so what that means is that now you can actually set up your differential equation for this problem. And so the differential equation for this problem is going to be the following. So in general, we have mx double prime plus beta x prime plus kx. This is equal to 0. But now we're going to replace the numbers. And so the problem that we do have is x double prime plus the beta is a number 10. X prime plus 16x is equal to 0. Right? So that is equal to 0. And so this is the differential equation that we get after translating the word problem into mass. Now, one other thing that we should also consider is uh, the initial conditions, and that is given by the remaining part of the problem. So it's released, the mass is released from 1 foot below the equilibrium position, and it has a downward velocity of 4 feet per second. And so what that means is that the original position, the initial position of the mass that is attached to the spring is given by 1 foot, because remember that in our situation that we're dealing with, we have a vertical axis, and then we said that the zero location is where the mass is located initially after you have attached the mass to the black spring on the ceiling. And so now what we're saying is that this mass has been stretched down to the location of 1 foot below the original position. And not only that, we also are given this a velocity, and the velocity is downwards. And so this is going to be equal to the number 4, positive 4, because downward for us in this axis is positive. Downward on the blue axis is positive. So this is positive x direction. All right, so what does that mean? Okay, so this means that we have the following initial value problem. So we have a differential equation, and then we have the initial conditions. Okay, so now how do we solve this problem? Okay, so let's just focus on the differential equation. So given that this is a second order linear differential equation, we're going to assume that the solution is of an exponential type. So this is going to be e to the rt. And now the question is, what is the value for r? That is what we're looking for. And so when you plug in this function into the differential equation, you get your auxiliary equation. So r squared plus 10r plus 16 is equal to 0. And now your task is to determine whether you can factor this or if you actually need to use the quadratic formula. Remember, we're trying to figure out what the r is equal to. And so if you can factor, that will be much faster than using the quadratic formula. So in this case, can we factor? And the answer is yes. So the answer would be 8 and 2. So those are the two factors. 8 times 2 is 16, and 8 plus 2 gives you 10. And that means that the two values that we get for this problem are equal to -8, and r is equal to -2. So we have two real numbers for this situation, and that's why we do know that this is the overdamped situation, which means that this is you're talking about the car suspension. This means that your car suspension is in good condition. Okay? So if you have two real numbers here, then that indicates that you do have a good suspension. Right. So now, given that we have two numbers, what are the two linearly independent solutions to this problem? So the two linearly independent solutions are going to be x1. So let me see. So x1 of t is going to be e to the -8t, and then the second solution is going to be e to the -2t. So they are exponential, and those are your two linearly independent solutions. And since we're trying to solve a differential equation, we want to write down the general solution to this problem. So it's going to be a combination of x1 and x2. And so I'm going to write that down on the next slide. So the general solution is going to be given by this combination of the x1 and the x2. All right. So now we're going to use the initial conditions. So we're going to use the first initial condition, and this tells us that when we plug in 0, the output is going to be equal to 1. So plugging 0 into this gray box function, then the output should be equal to 1. So if you do the algebra, then this will give you C1 plus C2 is equal to 1. So that's one equation. Now to use the second initial condition, we need to actually find the first derivative of this function. And so the first derivative turns out to be what? So this is going to be -8 C1 e to the -8t, and then minus 2 C2 e to the -2t. And so now looking at the second initial condition, we are saying that if we plug in 0 into this first derivative, the output should be equal to 4. And so let's do that. We plug in 0 into the derivative that we just found, and then we'll get the following. We get -8c1 minus 2c2, and then the output is going to be equal to 4. All right, so now let me simplify this slightly. So divide by -2 everywhere. So I'll get a 4c1 plus c2 divided by -2. This is going to be a -2 here. And so now I have this equation. This is a little bit simplified than the previous line. So now two equations, two unknowns. So we have enough information to solve for C1 and C2. And so what I'm going to do is I'm going to use the first equation. From the first equation, I get that C2 is equal to 1 minus C1. C2 is equal to 1 minus C1. And now I'm going to plug that information into my second equation. And so that tells us that 4C1 plus 1 minus C1 is equal to negative 2. All right, so now the C1s turn out to be 3C1, and then this is going to be equal to negative 3. So from this very bottom line, I go up, and then I get that C1 is equal to what? C1 is equal to the value negative 1. And now I use my second formula that I have up here on the very top. So that tells me that C2 is equal to 1 minus negative 1, and so that C2 is equal to 2. So C2 is equal to 2. All right, so now I'm going to put in these numbers into my general solution. And so my solution to the initial value problem is going to be the following. So it's going to be negative e to the negative 8t plus 2e to the negative 2t. All right, so this is the solution to your initial value problem. So this is what we say mathematically. This is the solution to the initial value problem. But now physically, we say that this is the equation of motion. So this is basically the equation that tells you how your car will be moving vertically up and down, or in this case, it actually just moves downwards, yeah, until it stabilizes. And so this is called the equation of motion. So this is the equation of motion for technically for the spring, but since the spring we are assuming that it's attached to the car, we are saying that this is the vertical motion of the car. All right, so this is the first example, and this is just an example for the overdamped situation. And now for the second example, what I'm doing is, that I have the same setup as before, but all I'm changing now is that the damping force is now numerically equal to 8 times the instantaneous velocity. Before, it was equal to 10 times the instantaneous velocity. So we have reduced the damping force. So going back to the car suspension, the damper on the car, it has a smaller damping coefficient. That's what we're saying. So going back to let's start from the very beginning. Okay, so going back to square one. So a 32-pound weight. So just from that, we remember that weight is equal to mass times gravity. So that means that 32 is equal to mass times the gravity. In this case, is going to be 32 feet per second. And so that we said that the mass is equal to 1. Then we talked about the spring coefficient, and that was using the Hooke's law. And Hooke's law says that the force that the mass does on the spring is equal to K times the stretching. And we said that the force in this case is 32, and then the stretching is 2 feet. And so we said that the K is equal to 16 as before. But now the damping law, and actually it can be more general, but we call this the damping law. We said that the damping law is equal to negative beta x prime, so proportional to the velocity, and it's actually on the opposite direction of motion. But the problem is telling you that the beta is equal to the number 8. Okay, so that means that we're going to set up our equation, and remember that the equations always have this format. So mx double prime plus beta x prime plus kx, this is equal to 0. We plug in our numbers, and then we get x double prime plus 8x prime plus 16x is equal to 0. And so now we have this differential equation, and now everything else stays the same. So the second part of the second sentence here tells us that the initial condition is again equal to 1. The initial velocity is equal to 4. And so now we have a differential equation together with 2 initial conditions, and so we should be able to solve this mathematically. Okay. So I've rewritten here on the very top the differential equation, and so let's focus on this. We assume that the solution, let's just do the work as before. So we assume that the solution is an exponential function, and so plug this into the differential equation, and then comes out your auxiliary equation. So r squared plus 8r plus 16 is equal to 0. And so now your task is to determine whether you can factor this or if we have to use the quadratic formula. And remember, at the moment, our question is, what is the value for r? What is the value for r? And so we either want to factor if we can, or use the quadratic formula. In this case, we can factor, and the factors are what? So it will be r plus 4 multiplied by r plus 4 is equal to 0, because 4 times 4 gives us 16, and then 4 plus 4 gives us 8. And so that means that we get the number r is equal to -4 and r is equal to -4. So we have repeated roots, and so mathematically we say that this is repeated roots, and then we say physically we have the critically damped situation, which means that the struts on your car, they're about to go out. Okay, so you might want to change them sometime soon, but if you don't, it's kind of okay. All right, so now what are the linearly independent solutions to the mathematical problem? So we have the differential equation, and then we said that we found the two roots to the auxiliary equation, and that means that the linearly independent solutions are going to be the following. So the first function is going to be e to the -4t, and now the second solution is going to be very similar. So it's going to be e to the -4t, but we have to attach this extra t. Okay, and remember, to get from the first solution to get the second solution, that's where you do the reduction of order method. If you want to practice, you can. But at the moment, we're just writing down our linearly independent solutions. All right, so now that we have our linearly independent solutions, the general solution to the differential equation is going to be the combination of x1 and x2. So let me write that down on the next slide. So the general solution is given by this combination. And now we're going to use the initial conditions to figure out what C1 and C2 are. And so the first initial condition tells us that if we were to plug in 0 into this formula, then the output would be equal to 1. And so we're going to do that. We're going to plug in 1 into the x formula. And if you do that, then you get this C2 times 0 is equal to 1, and which means that the C1 is equal to the number 1. So far, this is easier than the one before. But now, to use the second initial condition, we need to find the derivative of the x function. And in this case, the derivative, we have to be a little bit careful because this is a little bit more involved. So we have c1 multiplied by the -4 e to the -4t, that's the first part, plus c2. And what I'm going to do here, I'm going to write down the product rule, because we have two functions being multiplied, t multiplied by the exponential. Two functions being multiplied, so you have to use the product rule when you differentiate. So it's going to be the first one multiplied by the derivative of the second one, which is a -4 e to the -4t, plus the second function multiplied by the derivative of the first, which is going to be 1. And so that is the derivative on the very bottom. And now you don't need to simplify this, because remember, we're going to use the second initial condition. And so when you plug in the 0 into the derivative that you just found, you are going to make the whole thing equal to 4. So plug in 0 into the first derivative that you just found, and then what do you get? You're going to get -4c1 plus, and now this is going to be c2. This t, you're going to plug in a 0 there, so that first term goes away, and then the second term this is going to be +1, and so technically you just have a 1, and then you're going to make this equal to the number 4. Okay, you're going to make this equal to the number 4. And so what does that mean? Okay. So recall that you also know what the C1 value is. Okay, so C1 value is here on the first line in the gold box now. And so now you're going to replace that into your red equation on the bottom. And so that's a 1. And so C2 is going to be 4 plus 4, which gives you 8. So C2 is equal to 4 plus the 4, which gives you 8. So you have your two values for C1 and C2, and that means that you can write down your solution to the differential equation. And let me put that in blue. So the solution to the initial value problem turns out to be C1, which is a 1 e to the -4t, and then plus 8t e to the -4t. All right, so that's your solution to the problem. And mathematically, we're done with the problem, but now again, physically, we want to say that this is the case where you have critical damping on your system, which means that your suspension is kind of that you do a little bit of fixing on the car, on the suspension. All right, so now let me go into the last example. And so the last example is going to be the same problem, except that now I'm changing the damping even further. So I'm reducing the damping force even further. And so this is going to be only 4 times the instantaneous velocity, okay? And so let me just write down the information that we had previously, because it is the same problem as before. We found out that the mass was equal to 1. we found out that the K, the spring constant, was equal to 16. And then we are saying here that the beta is equal to the number 4. Okay, so those are the parameters coming from the physical situation. And now the equation that we get is always the same. So mx double prime plus beta x prime plus kx is equal to 0. We plug in the numbers, we get x double prime plus the beta is equal to a 4, x prime plus the k 16x is equal to 0. And so now we have this differential equation, and the initial conditions are the same as before. The initial position is equal to 1, and the initial velocity is equal to 4. And so now we have a system. We have an initial value problem, and we want to solve this differential equation. So let me just write this down on the very top. So we have the differential equation to be this with the initial conditions. And so now, again, we assume that the solution to this differential equation is going to be an exponential function. And so when you plug this into your differential equation, out pops out the auxiliary equation, which is r squared plus 4r plus 16 is equal to 0. And now the question is, can you factor this? And then if you cannot, then you can always rely on the quadratic formula. So here we are going to rely on the quadratic formula. The solution to this guy, because remember, we're trying to figure out what the r is equal to. We don't know what the r is equal to. And so the quadratic formula tells us that this is equal to negative b, which is negative 4, plus or minus the square root of b squared, which is 16, minus 4ac, which is a 16. Divide the whole thing by 2a, which is just 2. Now, if you simplify this a little bit, then you get negative 2 plus or minus, and then this becomes a square root of negative 3 times 16. Divide the whole thing, the square root part, by 2. Okay. So I simplify a little bit here. So the negative 2 in the beginning in solid black, that's by itself. And the division sign is only under the square roots. And so if you simplify this a little bit further, then you get the following. You get negative 2 plus or minus, and then this will be the square root of 16 is 4, but then 4 divided by 2 gives you 2. So this is 2i square root of 3. 2i square root of 3. So now you see that you have complex numbers. So this is the third case. Mathematically, this is the case where you have the discriminant to be negative. Physically, this is the case where you have a system that is underdamped. And underdamped, going back to the car example, means that the suspension on your car is bad and you actually need to replace it. So this is not a good thing if you're talking about a car suspension. In other physical situations, you might want to have underdamped situation. All right, so now what are the solutions to this problem? Okay, so what are the two linearly independent solutions? They are going to be, so let me write down x1 is going to be e to the negative 2t multiplied by cosine of 2 square root of 3 multiplied by t. So that's the cosine there. And then the second solution is going to be e to the negative 2t sine of 2 square root of 3t. So those are the two linearly independent solutions to the differential equation. And now we want to write down the general solution, which is going to be the combination of x1 and x2. And that's going to be written in this way. So this is the combination of x1 and x2. And now we're going to use the initial conditions here. Okay, so we want to use the first initial condition, and then this means plug in 0, the output should be equal to 1. So if you were to plug in 0 into this equation, so plug in 0 into the sine part, that entire term goes away. So you can actually just eliminate that. If you plug in 0 into the cosine of 0 is equal to 1, and then e to the 0 part is equal to 1. And so this is telling us that C1 is actually equal to 1. Remember, we made the whole thing equal to 1 after we plug in 0. And so we get that the value for C1 is equal to 1. All right, so that's the first constant. Now we want to use the second initial condition, but in order to use this second initial condition, we need to find the derivative of this x function. Here I typed it up because it gets a little messy. So this is the derivative of the general solution, and all I've done is, let me just break it down here. So this is the first function, and I have to use the product rule because you have the exponential function and then you have the cosine function, and so you have to use the product rule. So that's the derivative of the second one plus the second one to the derivative of the first. And now that's only the C1 parts, but then you also have the C2 parts. So you have the exponential part and then you have the sine parts. And so the derivative of that second term will be the first function times the derivative of the second one, plus the second function times the derivative of the first. So you can double check that this is the derivative of the x function. All right, so now we want to use the second initial condition here. And that means that if we plug in 0 into the formula, the output is going to be made equal to 4. But now, if we plug in 0 into the formula, notice that if we plug in 0 into the sine function, if sine of 0 is equal to 0, so that first term goes away. Now, same thing on the other one. So plug in 0 for the t. This is sine of 0, so that term also goes away. So that's nice for us. But now, what if you plug in 0 into the cosine? So this is cosine of 0. Cosine of 0 is equal to the number 1. And now e to the 0 is also equal to the number 1. Same thing on the bottom part. Cosine of 0 is equal to 1. And e to the 0 is also equal to 1. And so what does that tell us? That tells us that, so let me write it out this way. C1, and then the second box simplifies to -2, plus C2, and then the second box, square bracket, that is going to simplify to 2 square root of 3. And now we are going to make this equal to the number 4, because we are using the initial condition. So now we made this equal to 4. And now, do you remember what the C1 was equal to? Okay, so this is where we have to recall what the C1 was equal to. So C1 was equal to the number 1 after we use the first initial condition. And so we're going to plug that into our problem. And so that will be a -2. And so 4 plus 2 gives us a 6. And so this is going to be 2 square root of 3 multiplied by C2 gives us a 6. And if you simplify this, this gives us a C2 is equal to 6 divided by 2 root 3. And if you simplify, this will eventually be square root of 3. So do the algebra, and then you get the C2 is equal to root 3. So you have your C1 value, and then you also have your C2 value. So that means that you can write down your solution to the differential equation. And I'll write this on the very top. Okay, so I'll write this to the very top. And so the solution to this differential equation, to the initial value problem, is going to be C1 is 1, which is e to the -2t cosine of 2 square root of 3t. And then the C2 is the square root of 3. So this is e to the -2t sine of 2 square root of 3t. So very lengthy to write down, but I'm just plugging in my C1 and C2 into my general solution. All right, so we have solved the problem. And so the function on the top in red, that is the solution to the initial value problem. And then the other thing that I want to say is that this solution, this red function describes the behavior of your car as time progresses. How would the car be moving up and down vertically? How would the car be moving according to this function? Okay, so it's not so obvious, but eventually this is telling us that the car will be bouncing up and down. It will slow down, the bumping will slow down, but the car will be moving up and down, so you will feel a lot of wavy movement to your car, which it indicates that your car does need new struts or new shock absorbers or new springs. So just some physical example, just to give you a feeling that this is actually applicable to real life situation. All right, so that's all I have for today. There's a little bit more discussion to this last case, but I will make a separate video to talk about the amplitude, to tell you that for this red function on top, you can actually change the format of the function so that you can actually determine the amplitude of the movement of your car moving up and down, and then you can also determine the period, or what's called the quasi period, and also the other things called the quasi frequency. Okay. So that's going to be for a different video, but I hope that this example with the car suspension helps visualize that we are doing some practical mathematics here. All right, so that's the free damped motion. The entire discussion was about the free damped motion, and then we got 3 separate cases. One was where the car suspension was good, 2 was where the suspension was in a critical condition, and then 3 where the suspension was bad and you need to replace something. All right, so that's all I have for today. I hope you enjoyed this, and I'll see you next time.